Let's see, make sure everything is working. Hello? Hello? Testing, testing, 1, 2, 3, testing. I hope people can hear me. Let me just make sure. Hmm. Hmm. All right. Let's see. No. Hmm. Hmm. Let's see. Nick, let me see if I can. Nick, I just sent you. Oh, okay. Well, I just sent you a specific invite if you want to chat. There's a private GChat. This exchange that we have is public. Everybody can see it. Okay. I want to see if. Copy. Paste. Looks like they do not allow pasting. Okay. All right. All right, snow is falling. Students were saved. I'm back. Got a cup of tea. All right. I'm back. I suspect people can hear me. I know Nick is on. Nick, can you hear me? Ooh, nice. Let's see who is on. Ah, cool. 7 people. Awesome. We're going to see if this works. All right. Sheen, Nick. We got 8 people on. Nice. And probably a few hundred others from the Middle East and from China or some other place, which would be cool. Get a lot of people on. People won't have any idea about what we're talking about, but that's all right. This is designed for us. Oh, we lost people. All right. We'll start at about 3:05. Hopefully everybody is able to join us. And if we only have 6 people, I'll send out a hangout where we can be more interactive. Because this is just one-sided, and that's not great. This class is really about interaction. And I'm checking to see. One more minute and we'll begin. Oh, yeah. All right, 3:05. That's close to a minute. All right. 9 people. All right. All right, checking. If we cap out at 9, I'm going to go back to a regular hangout. All right, let's see. Staying at 9. I might go to a regular hangout, which would be very, very cool. All right. Oh, that's a good sign. All a good sign. Anybody joining me? Can people join me? Try clicking on that hangout and see if you can join me. Because that would be pretty freaking cool. Because I could stream this live. Helen's on. Carl's on. Can you guys hear me? Let's see. Ah, Amy's on. We got morning people showing up. This is cool. All right. Can you guys hear me?
Yeah.
Bitchin'. All right. Thank you. Whoever said that, I appreciate it. It's very loud.
Oh, yeah, and I just have my headset on too. So.
That's all right.
I just blasted my ears though.
Oh, crap. Okay, I'm going to see if.
Why is it still so loud?
I don't know. Might be me. I am kind of deaf, so I end up screaming a lot. Sorry. Amy didn't get enough of me just from this morning, so she's coming back for more. Now that's either an indication that I was ineffective this morning, which can very well be the case, or she loves regression and really wants to get this down. I'm hoping it's the latter, but I think it's more likely the former. sorting out some details. People are trying to connect. Let's see, who do we have? Nick and Carl, Helen, Gulner, Amy, Nushin, and me. Cool. All right. So for this afternoon, I assume everybody is not driving. We don't do these things while people are driving. I don't want you taking your eyes off the road, especially while it's snowing. People are nuts here. So this afternoon, what I intend to do is to talk a little bit about what I have in mind for you manufacturing your data, why you need to do it, and how you need to do it. Now, I don't want to answer the questions because one, I only got 3 of them, and I'd prefer to do that live. I'm assuming on Thursday we will not be meeting this way, so that will be a good thing. I will answer those questions in a more interactive format because oftentimes my answers bring up more questions, and that would be good. So in lieu of answering those 3 paltry questions, it leaves me to now say, and ask questions, everyone. Ask questions. I put that form up because this class relies upon you asking questions. If you don't ask questions, then I don't have anything to tell you about and just leave you up to your own devices. And my suspicion is you guys are not all knowing and know exactly what's taking place. My suspicion is that either A, you're not doing the reading, 2, you don't give a shit, or Roman numeral 3, you have no idea what you're doing, you haven't read the syllabus, and you're not paying attention to my directives. I hope all 3 of those are wrong and that you're just knowing all of this stuff cold. But please, 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 you need to ask questions. I'm sure that what you read in Cohen and Cohen is not perfectly clear. I read Cohen and Cohen many times. I know it ain't perfectly clear. All right. So today, instead of answering questions, I'm going to focus on talking about how and why to manufacture data. So as I said before last week, what I really wanted you to do is to start with generating 2 variables that have different correlations than 1.0. And the way I talked to you about it was focus on classical test theory. That is, observed score variance equals true score variance plus error. Now, the reason why that's relevant is because that's the heart of what I'm having you do. And what I'm having you do is something along the lines of manufacturing data based upon classical test theory. Now, the way I have you do that is I have you create a single variable. You'll see this in my code. I shared my screen with everybody, and you'll see that I start out, I highlighted the wrong line. I generated a random normal variable. It just so happens that in R, this R norm function creates a random normal vector that is a series of values with a mean of 0 and a standard deviation of 1, unless I specify otherwise. So essentially, that's the mean of 0 and a standard deviation of 1. But if I leave that out, it's just assumed to be 0 and 1. Now, what I asked you to do last week was to create a variable. Oh, great. Okay, we got another person. Nice. Nice. That looks like Aziz. Cool. All right. I had you last week create a variable and then create another variable or 2 with different correlations. All right, cool. Those different correlations are such that you can create and you can change the magnitude of the correlation by understanding classical test theory and the parts that you're mixing together. So in week 1, I gave you this code, and I talked about creating a base variable and then Carrie says, can't get the, all right, hold on a second. 1, 2, 3, 4, 5, 6, 7, 8. All right, give me a second. Hold on a second. I have to send out an invite. Okay, sorry, having to invite people via the YouTube live. Okay, so I asked you to create a base variable, and then from that base variable, add noise. And what you did was, most people did this, where you created that X and Y variable by sharing the same common variance. And so that's essentially the same variable. And then you added noise. Now one thing that I want to emphasize is that variance is additive. Okay? So I'm typing this out so that you can see. Variance is additive. So when I use, oh, looks like, did we gain? No. We gained somebody. Don't know who. When I have one part, okay, one part that is reliable, variance, plus one part random error, that is our norm, we have reliability that equals 0.5. Okay, it looks like we, all right. Carrie?
Yes.
All right, welcome.
I made it. Thanks.
Okay, so when we have, because variance is additive, we have one part reliable variance plus one part random error, which means that we have a reliability of 0.5. Now, why 1.5? Because true score theory posits that reliability is equal to true score variance divided by observed score variance. Okay? And that's nothing more than saying that reliability is equal to true variance divided by true variance plus error variance. Now, what are we doing with this? We are saying this is true and this is error. This is true and this is error. So this one has a reliability equal to 0.5. And this one has a reliability equal to 0.5. Now, because in classical test theory, we are talking about variances, and variance is additive, we need to think about how we are communicating correlations with respect to variance. Correlations have to do with standard deviations. Coefficients of determination, little r squared, have to do with variances. Okay? Now, the maximum correlation that you can see from two variables with reliability of 0.5 is not easy to calculate. The maximum coefficient of determination equals the reliability of X times the reliability of Y. Oh, yeah. Carrie, can you mute your microphone?
Yes, how?
When you move the mouse over the screen, on the bottom, there's a little telephone. To the left of it has a microphone.
Got it.
Cool. All right. So the maximum coefficient of determination is the reliability of X. And I'm just going to mark this, reliability of X. So that means R squared is equal to, or it can be less than or equal to 0.5 times 0.5, where the correlation then is equal to the square root of R squared, which is going to be less than or equal to 0.25. How do we get that? Because reliability deals with variances, because reliability deals with variances, and the coefficient of determination deals with variances, we have to do like to like. Correlations are standard deviations, not variances. Hence, we have to go from like to like, take the square root of the coefficient of determination to find the maximum correlation. So when somebody asks you, what is the maximum correlation expected when you have two variables of reliability 0.5, you will see the maximum correlation is going to be 0.25, hypothetically. Okay, now what do I do here? Give me 1 second. I hate it when I do all of this in advance and then screw it up. 0.5. Oh, no, sorry. I screwed this up. Yes, yeah. Thank you. Is equal to 0.25. Thank you. Sorry. This is the way my brain is working on a snow day. Machine is awesome. She's keeping me honest here. So we multiply, and Amy, this is where I was screwing up this morning. You can see why I'm no longer a mechanical engineer. I would never design anything that people could walk through on or anything like that. Everyone would be killed. So start out with a sample size, have a base variable, add error to that base variable, do a correlation. Now the reliability is 1 part common, meaning 1 part that is reliable, 1 part noise. So because it's 1 part that's reliable, it's 1 over 1 plus 1, because the variance of the base is 1. By definition, because the default is mean equal to 0, standard deviation equal to 1. When you square the standard deviation of 1, it equals 1. Okay? Squaring standard deviation gives us variance. So this variance is 1, this variance is 1. So the reliability is this because it equals 1 over 1 plus 1, which equals 1/2 or 0.5. Same with both of these. Okay, now the reason why we're doing this is because I want you to manipulate I want you to manipulate the reliability of these variables such that you can change the course. Okay, now, because variance is additive, what we're doing is we're creating variability that can alter the error variance of each one of these. Now, I want to show you what I'm doing here and what I was trying to lead people to think about in the morning section, and I'm afraid that I probably made it more confusing. So in week 2, that's this week, we are talking about the same thing, but what I wanted people to do is to create a different set of variables. So you'll notice I have a sample size. I have a y variable, r norm again. X1 is just a point reliability equal to 0.5. Whoop. This one has a reliability that's slightly different, okay? Why is it different? Because I have something that I want the relationship between x2 and y, x1 and y to be of a known value, okay? So the only parts that I care about are the parts that include y. Now, because variance is additive, remember I said that here, variance is additive. Because variance is additive, we have here, this equals 1 over 1 plus 1, which equals 1 over 2, which equals 0.5. I love typing 0.25. I don't know why that is. Okay, so let's break this one down. What's the reliability of x2? That is the reliability of x2 of the variance that is likely to share with y. Let's look at that. So the y part is the reliable variance. Now, y contributes 1 unit variance, okay? Now, x1, I'm gonna create a fraction here, and I'm gonna say what parts of y and what are the total parts that we have. Okay, so now x1 has 1 y in it, right? I'm adding x1. So x1 has another part of y, so I have to add that to the numerator. And in the denominator, I'm going to add all of this up. Okay, so in the numerator, I've got 1 part y, and I've got another part y that comes from x1. Now, x1 has a variance of 2. How do I know that? Well, let's do it. What is the variance of y? It's going to be roughly 1. What is the variance of x1? It's going to be roughly 2. Why is that? Because x1 has the variance of y right here. Remember, this has a mean of 0 and a standard deviation of 1. Okay? Now, because of that, every time you add an R norm, you're expanding the variance. You're expanding the variance. Variance is additive. So the variance of y alone is 1. The variance of x1 is 2. 1.98 is 2 in my book. Okay? Now, these are random normal variables so that you know that there's a little error in it. Okay, now, what happens if I add a new random normal variable? Here is the signal for x3. I'm adding 1 part y to how many parts of error am I adding? Anybody know? Anyone? What's x3 going to equal? What's the variance of x3? Okay, Nick guessed 3. Anyone? Okay. Machine guessed 1. Anyone? Others? All right, ready? 10. 9.9 is 10. Remember, you're losing a little bit. Why 10? Why 10? Well, this part here, remember, this is the mean, and this is the standard deviation, not variance, standard deviation. Standard deviation is not additive. Variance is additive. So the variance of our norm N03, the variance of that is 9. So we're adding 1 part signal to 9 parts noise, meaning that the total variance is 10. The total variance is 10 for X3. The total variance is 10. Now, the total reliable variance is 0.1. Okay? Totally expected. We have a correlation that is 0.32. Now, we couldn't have predicted that unless you're really good at math in your head. But we could have predicted that. That's the coefficient of determination. We do know that the reliable variance is the upper bound for the coefficient of determination, not for the correlation. Coefficient of determination deals with variance. Correlation deals with standard deviations. We are manipulating variance. So when we're manipulating variance, you have to have like to like. So square the correlation, and that tells you the maximum coefficient of determination between 2 variables, one variable y that has a reliability of 1.0, and another variable X3 that has a reliability of 0.1. So multiply 0.1 times 1, and that tells us the maximum coefficient of determination expected from that relationship between y and X3. So when you're manipulating data, you're manipulating error variance by adding more error variance. And you can do that by just changing the amount of variance that you have in your addition. Okay, now, many of you are asking about how do you do this in SPSS? Turns out that you can do it quite easily in SPSS because this random variable allows you to specify many different values where you have the mean and standard deviation. I'm just going to copy this. That's the code that's used in SPSS. Now, there is a new method for doing this. This is a little dated because the new method allows you to create more cases. So let's do this. Give me a second. Ever finish going through X2? Probably not. Sorry, Amy, I was looking elsewhere. X2. Amy asked about X2. X2, I skipped over to X3 because X3 is a little bit easier. Now I'm going to go back over x2, okay? So x2, x3 has a reliability of 1 over 10. Why? Because that's 1 divided by 1 part reliable over 9 parts noise, which equals 0.1. Now let's go back over x2, because x3 is a little simpler. x2 has 1 part y in here and 1 part y here. So we have to have 1 and 1 in the numerator because that's the y part. Okay. But now how many total parts do we have? We've got 1. Remember, the variance of x1 is 2. Okay. So we've got 1 plus 2 plus 1. So that should equal, that should equal 2 over 4, which equals 0.5. Okay? Now, that isn't necessarily the case, because x1 is a weird variable that's really embedded with y, and that's okay. So we have 2 random independent noise sources that are coming in. So let's look at the correlation between y and x2. Okay, it's 0.81. All right. When we square that, that gives us the coefficient of determination. And what you're seeing is that the correlation between y and x2 isn't as simple as simply adding the noise to the signal, because we're adding the signal of y to x2 as a part of x1. And here's where making these data sets becomes somewhat more complicated. It becomes more complicated because we're adding different layers to our data set. Okay, so x2 is more complicated. We would expect the maximum correlation to be somewhere around 0.7. Okay, why 0.7? Because the amount of reliable variance that is between x2 and y is going to be somewhere in the neighborhood of a combination of just y that is measured perfectly, and x2, which is measured imperfectly, but imperfectly with another variable nested in it. So we would normally think that it's 0.5, right? 0.5 times 1, which is the reliability of y. So we're thinking that it's 0.5. And with 0.5 being the maximum coefficient of determination, we would expect the maximum correlation to be about 0.7, but it's not that easy. As soon as you start nesting variables in, we start getting unpredictable relationships. And that's okay. We're going to make these relationships somewhat unpredictable by making our data sets complicated. Okay? By making our data sets complicated, we're simulating more real life data. I would recommend early on making variables that are controlled this way and this way before creating multicollinearity this way. Okay? Certainly when you get to a variable like this, now we have a lot of error variance that's coming in all different directions. The reliability of this one is way more complicated. Why? Because x4, all we care about is the correlation between y and x4. Okay, so the key is the signal is in the y. Well, there's 1 part y, so we're going to do We're going to do the same ratio. So there's one part of signal that's reliable variance from the Y alone. And then we get another part of Y from X1, right? Because there's a Y in X1. Plus we get another part of Y in X2, right? Except for the fact that X2 isn't complete because X1 has both Y and noise in it. So X1, we're not going to call a complete one. We're going to call it 0.5, okay? And that's where things get complicated. We're going to go over these ratios of variances in detail because you need to understand this when we talk about B's being partials and semi-partials. And what we're going to do is we're going to talk more about exactly how many parts we have in here, how many reliable parts, because X1 has a variance of 2. So in part of reliable variance of Y, X1 part that's reliable variance of Y, so we'll add the X3 being a reliable part. So we've got 3 parts of variance: a variance from X1, a variance from X2, and a variance from X3 that are all part of Y. Now, what do we do with the denominator? That's the total variability. Well, the variance of Y is 1, but the variance of X2, oh, excuse me, of X1, I don't want to jump. The variance of X1 is 2. The variance of X3 is what? What's the variance of X3? Remember, going back to the example that I had? Yes, Yushin's spot on. The variance of X3 is 10. All right. And then we add another because we're getting a random normal vector that's being added to this with a mean of 0 and a standard deviation of 1, which means the variance is 1. So what is this total value? Okay. So the reliability is equal to 0.21, which means the coefficient of determination should be a maximum of about 0.2. So when I do a correlation between Y and X4 and I square it, that's the coefficient of determination, I get 0.6. Why am I getting 0.6? Because I'm adding lots of complicated pieces. These Y pieces turn out to be not as full as we expect, okay? And that's why what I was saying before is these are simpler formulas to add error variance. These get wicked complicated because we're starting to add more complicated variance that is both signal, true score variance, as well as error variance. So the reliability of 0.21, we'd expect the maximum coefficient of determination to be about 0.2. And because of that, I would expect the maximum correlation to be about 0.45. Instead, we are getting coefficients of determination that is 0.6, meaning that there's a lot more complexity to this multicollinearity than exists in just the manufacturer. We're going to talk about this at length when we go back to partials and semi-partial correlations. For now, I want you to take away that the variances are additive, standard deviations are not. Always do like to like. When you're doing variances, always take variances back to variances. Meaning anytime you're manipulating variances, error variances, reliability deals with variances. Reliability is the ratio of variances. It is the true score variance or the observed score. That's all I'm doing here. I'm doing all of this, true score variance over observed score variance. I am creating ratios of variances. Now, correlations are not variances, they're standard deviations, but the coefficient of determination is a ratio of variances. It's a ratio of the variance of X as it pertains to the ratio to the variance of Y. It's how much variability in X is observed in Y. Now, think back to what a correlation is. The correlation is the line of best fit between a standardized X and a standardized Y, or a standardized X1 and a standardized X2. So all we're doing is we're manipulating reliability to be able to understand and appreciate and to be able to predict what the coefficient of determination is, and then you take the square root of that and you get the maximal or expected value of the correlation. So today what I want you to do is I want you to step through a bunch of these, and I can show you what I did here is I did a very simple loop where I went from a standard deviation of 1 to a standard deviation of 10 to show you that by manipulating the standard deviations, I did a little for loop, and the for loop allows me to step by step go through different standard deviations, collect it into a data set, and then plot it. And the plot shows me, let's see, does this show up? No, of course it doesn't. This plot right here shows me that as the standard deviation of the error variance increases, the expected correlation decreases. And it decreases as a, remember, as a square root function, okay, as a square root function, because these are correlations. Now, the other thing I could do is I could square this so that it's a little bit easier to see. And by doing that, I will show you that it is still, this is the coefficient of determination. Okay, I've just squared it because I did that here. And I'm just showing you the plot values for as the variance increases, so does the error variance, thus attenuating the relationships between two variables. All right. So this is something that I want to emphasize because this is a tool we are going to be using throughout the semester. We are using this tool to manufacture data because right now I just want you to manufacture data that's simply manipulating the level of error variance. Soon we're going to move over to creating greater multicollinearity. Therefore, you're going to create relationships between your predictors such that they are confounded or collinear with Y. And then we're going to talk more about how to deal with that. Okay, we're going to change the values that we have in our relationships. We're going to change the values we have in our data set to create outliers and influential values. We're going to do all of this because you're going to be able to do this either in R or SPSS. Okay. For SPSS users, I apologize because I don't have SPSS. You can see I'm running all of this through Linux, or actually through the web browser even. The RV normal is the thing that you can use to create means and standard deviations in your data sets. And you can do that by just simply adding, you can follow pretty much the same code that we have here, and you can create these data sets with relative ease. Okay, remember that if you're using SPSS, you've got to use syntax. There's no point and click for this stuff. Okay, this morning we don't have many SPSS users in the morning. People were, the few that were there were trying to use this compute variables dialog box. Do not use that. It is not useful. You need to use syntax. Okay, if you're unfamiliar with syntax in SPSS and you find it arduous to be able to use the syntax, I recommend that you shift over to R now. You'll have to learn syntax in R or SPSS. SPSS, learning how to do syntax and SPSS will not make you more marketable or employable, but learning how to program in R will make you more employable and marketable. Okay, so end of plug for that. All right, I'm done screen sharing. Everybody understand what we're talking about here? Clearer, less clear, totally confusing? More clear. All right, cool. All right. Anyone else? Yeah, good. All right, cool. Cool. And Nick, I know that you're new to using R, so I hope that you're finding this to be a little bit easier. I can post all of these code snippets to people if you so desire. Because you guys are here, I can just do this. You'll hate the way this comes out. Yep, Nushin, I just pasted that in. Apologies, that's the way it posts. How about this? I'll take a screenshot. Give me 1 second.
Question. Can you hear me?
Yeah, I can hear you loud and clear.
Yeah, so RV normal, you kept mentioning RV normal, but I'm very new to R, so I was wondering if that's something you created to explain, or is that a code that we use in R?
RV normal?
Yes.
It's for SPSS users.
Okay. But if I use R, do I still need that, or?
Not if you're not using SPSS.
Okay.
It's only SPSS.
Gotcha.
Okay. All right. Hold on a second. Give me a second. I'm going to attach a file. Okay. I'll send the file out. Oh, let's see. Oh, I guess I had this all along. Google. There we go. Here is the R code from today's sent. Ta-da! We have the technology. I guess we still have to use email every so often. All right. So I think we can adjourn now. We didn't have everybody, but that's okay. Looks like people are done.